open the table of content first. Alright, we are still in chapter 23. The last session we take a look at, or the previous session we take a look at VAX/VMS virtual memory, and now let's take a look at the Linux virtual memory system 23.2. Let's check this out. Maybe we can do this. Let's see. Okay, this is the Linux virtual memory system. We'll now discuss some of the more interesting aspects of the Linux virtual memory system. Linux development has been driven forward by real engineers solving real problems encountered in production, and thus a large number of features have slowly been incorporated into what is now a fully functional feature-filled virtual memory system. While we won't be able to discuss every aspect of Linux virtual memory, we will touch on the most important one, especially where it has gone beyond what is found in classic virtual memory systems such as VAX/VMS. Okay. We will also try to highlight commonalities between Linux and older systems. For this discussion, we will focus on Linux for Intel x86, where Linux can and does run on many different processor architecture. Linux on x86 is the most dominant and important deployment, and thus the focus of our attention. Alright, so we will focus on the Intel x86 architecture. Right. The Linux address space, much like other modern operating system, and also like VAX/VMS, a Linux virtual address space consists of a user portion. Okay, there's a footnote here. Until recent change due to security threats, that is. Okay. Read the subsection below about Linux security for detail on this modification. Okay. Linux virtual address space consists of a user portion where user program, code, stack, heap, and other parts reside, and a kernel portion where kernel code, stack, heap, and other parts reside. Like those other systems, upon a context switch, the user portion of the currently running address space changes. The kernel portion is the same across process. Okay. Upon context switch, the user portion of the currently running address space changes. The kernel portion is the same across process. Like those other systems, a program running in user mode cannot access kernel virtual page. Program running in a user mode cannot access kernel virtual page only by tapping into the kernel and transitioning to privileged mode can such memory be accessed. In classic 32-bit Linux, that is Linux with a 32-bit virtual address space, the split between user and kernel portion of the address space takes place at address. Okay, this one. The split between user and kernel portion of the address space takes place at this address, or 3/4 of the way through the address space. Thus virtual address 0 through this one. Oh, our user virtual address. Okay. The remaining virtual address, this one until this one, the 32-bit, I guess, and in the kernel's virtual address space. 64-bit Linux has a similar split but at slightly different point. Figure 23.2 shows a depiction of a typical simplified address space. One slightly interesting aspect of Linux is that it contains two types of kernel virtual address. Two types of kernel virtual address. Okay, the first are known as kernel logical address. This is what you would consider the normal virtual address space of the kernel. Okay, to get more memory of this type, kernel code merely needs to call kmalloc. Okay, most kernel data structure live here, such as page table, per process kernel stack, and so forth. Okay, unlike most other memory in the system, kernel logical memory cannot be swapped to this. Okay, kernel logical memory cannot be swapped to this. So this kernel logical address cannot be swapped to this. Alright. The most interesting, well, I assume this kernel logical address is the, what is it called? The important part, maybe something like that. That's why the memory cannot be swapped to this. Maybe. The most interesting aspect of kernel logical address is their connection to physical memory. Specifically, there is a direct mapping between kernel logical address and the first portion of physical memory. Oh, interesting. Thus, kernel logical address, this one, translate to physical address. Oh, right. This, okay. Calculate this one and this one, translate to physical address this one, and so forth. This direct mapping has two implications. The first is that it is simple to translate back and forth between kernel logical address and physical address. As a result, these addresses are often treated as if they are indeed physical. The second is that if a chunk of memory is contiguous in kernel logical address space, it is also contiguous in physical memory. This makes memory allocation in this part of the kernel address space suitable for operation which needs contiguous physical memory to work correctly, such as input-output transfer to and from device via direct memory access, DMA. Okay. This memory allocated in this part of the kernel address space suitable for operation which needs contiguous physical memory to work correctly, such as input-output transfer to and from device via direct memory access, or DMA, something we will learn about in the third part of this book. I assume maybe this one, persistent. I mean, this is the first part, right? Virtualization. The second part is concurrency. The third part is persistent from the 3 ECPs here. Okay. The other type of kernel address is a kernel virtual address. Okay. To get memory of this type, kernel code calls a different allocator, vmalloc, which return a pointer to a virtually contiguous region of the desired size. Alright. Unlike kernel logical memory, kernel virtual memory is usually not contiguous. Its kernel virtual page may map to non-contiguous physical page and is thus not suitable for direct memory access. However, such memory is easier to allocate as a result, and thus used for a large buffer where finding a contiguous large chunk of physical memory would be challenging. In 32-bit Linux, one other reason for the existence of kernel virtual address is that they enable the kernel to address more than roughly 1 GB of memory. One of the reasons for the existence of kernel virtual address, they enable the kernel to address more than 1 GB of memory, roughly, right? Okay. Years ago, machine had much less memory than this, and enabling access to more than 1 GB was not an issue. However, technology progressed, and soon there was a need to enable the kernel to use larger amount of memory. Okay. Kernel virtual address and their disconnection from a strict one-to-one mapping to physical address to physical memory make this possible. However, with the move to 64-bit Linux, the need is less urgent because the kernel is not confined to only the last 1 GB of the virtual address space. That make me curious. Is the kernel logical address here allocate during the startup or the booting process? Yeah, I'm still not sure, and cannot be swapped to this apparently. And then I assume the kernel virtual address here be swapped to memory, maybe. I mean, it is the usual virtual address, right? Well, let's continue first, I guess. Base table structure, because we are focused on Linux for x86, our discussion will center on the type of page table structure provided by x86, as it determines what Linux can and cannot do. As mentioned before, x86 provides a hardware managed multi-level page table structure with one page table per process. The operating system simply sets up mapping in its memory, points a privileged register at the start of the page directory, and the hardware handles the rest. x86 provides a hardware managed multi-level page table structure with one page table per process. Okay. The operating system simply sets up mapping in its memory, points a privileged register at the start of the page directory, and the hardware handles the rest. The operating system gets involved, as expected, at process creation, deletion, and upon context switch, making sure in each case that the correct page table is being used by the hardware MMU, the memory management unit, to perform translation. At process creation, deletion, and upon context switch, okay, making sure in each case that the correct page table is being used by the hardware memory management unit to perform translation. Alright, probably the biggest change in recent years is the move from 32-bit x86 to 64-bit x86, as briefly mentioned above. As seen in the VIX/VMS system, 32-bit address space have been around for a long time, and as technology changed, they were finally starting to become a limit for programs. Okay. As technology changes, they finally starting to become a limit for programs. Virtual memory make it easy to program system, but with modern system containing many gigabytes of memory, 32-bit were no longer enough to refer to each of them. Thus the next leap became necessary. Moving to a 64-bit address effect page table structure in x86 in the expected manner, because x86 uses a multi-level page table. The current 64-bit system uses a 4-level table. Oh, 4-step. The current 64-bit system uses a 4-level table. Interesting. The full 64-bit nature of the virtual address space is not yet in use. However, rather only the bottom 48 bits. Thus a virtual address can be viewed as follows. Oh, this one is unused. Okay. As you can see in the picture, the top 16-bit of a virtual address are unused and thus play no role in translation. The bottom 12 bits, due to the 4 kilobyte page size, are used as the offset and hence just used directly and not translate. Oh. I am not sure. Let me try. 12. Oh. As to offset. Oh, maybe to offset for the page directory, something like that. So we are not using that 12-bit here. Oh, wait. Oh, sorry. I think this is the, what is it? The offset where we place the data, maybe something like that. That's why this is just used directly instead of translate. Okay. So this is something like page directory 1, page directory 2, and so on. And this is the, what is it? The offset where we place the data. The memory where we place the data. Maybe something like that. The P1 portion. Okay. Wait, leaving the middle 36-bit of virtual text to take part in the translation. Like this one. The P1 portion of the address is used to index into the topmost page directory, and the translation proceeds from there one level at a time until the actual page of the page table is indexed by P4, yielding the desired page table entry. The P1 portion of the address is used to index into the topmost page directory. Write this one. Topmost page directory, and the translation proceed from there one level at a time until the actual page of the page table is indexed by P4, yielding the desired page table entry, and then we get the data from this offset. We get the actual data by adding this offset, something like that. As system memories grow even larger, more part of this voluminous address space will become enabled, leading to 5-level and eventually 6-level page table tree structure. As a system memory grows even larger, more parts of this voluminous address space will become enabled, leading to 5-level and eventually 6-level page table tree structure. Okay. Imagine that a simple page table lookup requiring 6 levels of translation just to figure out where in memory a certain piece of data resides. Yeah, that is the interesting part. With this multi-level page table, right? Large page support. Oh. Okay. Intel x86 allow for the use of multiple page size, not just the standard 4 kilobyte page. Specifically, recent design support 2 megabyte and even 1 gigabyte page in hardware. Oh, interesting. 1 gigabyte page. Okay, thus over time, Linux has evolved to allow applications to utilize this huge page, as they are called in the world of Linux. Using huge page, as hinted at earlier, leads to numerous benefits, as seen in VAX/VMS. Doing so reduces the number of mappings that are needed in the page table. The larger the page, the fewer the mapping. Okay, the larger the page, the fewer the mapping. However, fewer page table entry is not the driving force behind huge page. Rather, it's better for the translation look aside buffer behavior and related performance gain. When a process actively uses a large amount of memory, it quickly fills up the translation look aside buffer with translation. If those translations are for 4 kilobyte page, only a small amount of total memory can be accessed without inducing TLP miss. The result for modern big memory workload running on machines with many gigabytes of memory is a noticeable performance cost. Research show that some applications spend 10% of their cycle servicing translation look aside buffer miss. Oh, interesting. Okay. Some applications spend 10% of their cycles servicing TLP miss. Okay. Huge page allow a process to access a large tract of memory without translation look aside buffer miss by using fewer slots in the translation look aside buffer, and this is the main advantage. Okay. However, there are other benefits too. Huge page, there is a shorter TLP miss path, meaning that when a translation look aside buffer miss does occur, it is serviced more quickly. In addition, allocation can be quite fast in certain scenarios, a small but sometimes important benefit. Right. I assume by increasing the page size, it become more quickly because we didn't have a lot of translation process, maybe something like that. For example, the trade-off with using multi-level page table here is that sometimes we need a lot of translation, like this one. Imagine we have a 5-level or 6-level page table. We need 6 levels of translation just to figure out where in the memory a certain piece of data resides. So maybe that is why when we have the TLP maze, using huge page can make it quicker, I guess, to what is it called? get the translation address, maybe something like that. In addition, allocation can be quite fast in certain scenario, a small but sometimes important benefit. One interesting aspect of Linux support for huge pages is how it was done incrementally. How it was done incrementally. Alright. At first, Linux developer knew such support was only important for a few applications, such as large databases with stringent performance demand. Thus, the decision was made to allow application to explicitly request memory allocation with large space, either through mmap or shmget call. In this way, most applications would be unaffected and continue to use only 4 kilobyte page. Okay. The decision was made to allow application to explicitly request memory allocation with large page, either through mmap or shmget call, system call. In this way, most applications won't be affected and continue to use only 4 kilobyte page. A few demanding applications would have to be changed to use this interface, but for them, it would be worth the pain. More recently, as the need for better translation look aside buffer behavior is more common among many applications, Linux developers have added transparent huge page support. What transparent in here means, I assume maybe it is something that we cannot see rather than openness. Maybe when this feature is enabled, the operating system automatically looks for opportunities to allocate huge space. Usually 2 megabyte, but on some system 1 gigabyte. That's a lot. Okay, that's huge space indeed, without requiring application modification. Okay, so I assume transparent in here means invisible, I guess. So the process won't even know whether we have huge page or normal page. Maybe something like that. Huge pages are not without their cost, right? The biggest potential cost is internal fragmentation. That is a page that is large but sparsely used, right? This form of waste can fill memory with large but little use space. Sweeping, if enabled, also does not work well with huge pages, sometimes greatly amplifying the amount of input-output a system does. Overhead of allocation can also be bad in some other cases. Overall, one thing is clear: the 4 kilobyte page size which served system so well for so many years is not the universal solution. One thing is clear: the 4 kilobyte page size which served system so well for so many years is not the universal solution. It once was, growing memory size demand that we consider large page and other solutions as part of a necessary evolution of the virtual memory system. Linux's slow adoption of this hardware-based technology is evidence of the coming change. Okay, there is page case. Wait, before continuing to the page case here, let me read the tip, I guess. Okay. Did I miss something? Not yet. Except for this one, I guess. Okay. Let's read the tip. Consider incrementalism. What? Oh. Many times in life, you are encouraged to be a revolutionary. Think big, okay, they say. Change the world, they scream. And you can see why it is appealing. In some cases, big changes are needed, and thus pushing hard for them makes a lot of sense. And if you try it this way, at least they might stop yelling at you. Okay. However, in many cases, a slower, more incremental approach might be the right thing to do. The Linux huge page example in this chapter is an example of engineering incrementalism instead of taking the stance of a fundamentalist and insisting large pages were the way of the future. Developers took the measured approach of first introducing specialized support for it, learning more about its upside and downside, and only when there was real reason for it, adding more generic support for all applications. Incrementalism, while sometimes called, often leads to slow, thoughtful, and sensible progress. When building systems, such an approach might just be the thing you need. Indeed, this may be true in life as well. Okay, let's continue the page case. Okay. To reduce cost of accessing persistent storage, the focus of the third part of this book, right, this one, persistence. To reduce cost of accessing persistent storage, most systems use aggressive caching subsystem to keep popular data item in memory. Linux, in this regard, is no different than traditional operating system. Okay, the Linux page case is unified, keeping pages in memory from three primary sources: memory map file, file data, and metadata from device, usually accessed by directing read and write calls to the file system, and heap and stack pages that compress each process, sometimes called anonymous memory, because there is no name file underneath of it, but rather swap space. Okay. primary source, memory map file data and metadata from device, usually accessed by directing read and write calls to the file system, and heap and stack pages that comprise each process, sometimes called anonymous memory because there is no name file underneath of it but rather swap space. Interesting. These entities are kept in a page cache hash table, allowing for quick lookup when set data is needed. The page cache track if entries are clean, read but not updated, or dirty, also known as modified. Okay. The page cache track if entries are clean, read but not updated, or dirty, or modified. Okay. Dirty data is periodically written to the backing store, that is to a specific file for file data, or to swap space for anonymous region. Okay. By background threads called ptflash. Okay. Written to the backing store by background threads, the ptflash, thus ensuring that modified data eventually is written back to persistent storage. This background activity either takes place after a certain time period or if too many pages are considered dirty, put configurable parameters. Okay. In some cases, a system runs low on memory and Linux has to decide which page to kick out of memory to free up space. To do so, Linux uses a modified form of 2Q replacement, which we describe here. The basic idea is simple. A standard LRU replacement is effective, but can be subverted by certain common access pattern. For example, if a process repeatedly accesses a large file, especially one that is nearly the size of memory or larger, least recently used will kick every other file out of memory. Even worse, retaining portion of this file in memory isn't useful as they are never referenced before getting kicked out of memory. Okay. The Linux version of the 2Q replacement algorithm solves this problem by keeping two lists and dividing memory between them. When accessed for the first time, a page is placed on one queue called A1 in the original paper, but the inactive list in Linux. Okay. When it is re-referenced, the page is promoted to the other queue called AQ in the original paper, but the active list in Linux. When replacement needs to take place, the candidate for replacement is taken from the inactive list. Okay, Linux also periodically move pages from the bottom of the active list to the inactive list, keeping the active list to about 2/3 of the total page size. This reminds me of the, what is it called? VM stack, I guess. Previously there is the active and inactive memory. Alright. Maybe this is what it means. The inactive list and the active list. And this also reminds me of the VAX VMS operating system, about the P1, where is it? P0 and P1, I guess. Yeah, this one. Oh, wait, no, not that one. The clean and dirty list. Where is it? Yeah, the clean list and the dirty list here. The clean is not modified and the dirty list is the modified page or something like that. See, if another process needs free page, it can text the first free page of the global clean list. And if the original process that need the previous page, something like that, they can reclaim it from the clean or dirty list, and thus avoiding this access. So before swiping to this, there's a second change list, something like that. But on Linux, maybe rather than second change list, it is the actual list, the main list, maybe, or maybe the same. Yeah, I'm still not sure. To queue replacement algorithm. Yeah, like for example, the active list. Is the active list the main queue or something like that? The main list? Yeah, I'm still not sure. Okay. Probably the active list kind of the main list, maybe. Yeah, let's continue first. There's a lot that I'm still not sure about. 2/3 of the total page size, page case size, or maybe it is just the page case, not the amount of memory used. Yeah, I'm still not sure. Linux would ideally manage this list in perfect list recently used order, but as discussed in earlier chapter, doing so is costly. Thus, as with many operating systems, an approximation of LRU similarly to clock replacement is used. These two queue approaches generally behave quite a bit like LRU, the list recently used, but notably handles the case where a cycling large file access occurs by confining the page of that cyclic access to the inactive list. Because that pages are never re-referenced before getting it out of memory, they do not flush out what the usual page found in the active list. Okay. Aside the ubiquity of memory mapping. Okay. Memory mapping predates Linux by some years and is used in many places within Linux and other modern systems. The idea is simple. By calling mmap on an already open file descriptor, a process is returned a pointer to the beginning of region of virtual memory where the contents of the file seem to be located. By then using that pointer, a process can access any part of the file with a simple pointer dereference. Access to part of a memory map file that have not yet been brought into memory trigger page fault, at which point the operating system will page in the relevant data and make it accessible by updating the page table of the process accordingly. That is demand paging. Okay. Access to part of a memory map file that have not yet been brought into memory trigger page fault, at which point the operating system will page in the relevant data and make it accessible by updating the page table of the process accordingly. Every regular Linux process uses memory map file, even though the code in main does not call mmap directly. Because of how Linux loads codes from the executable and shared library code into memory. Below is the highly abbreviated output of the bmap command line tool, which shows what different mapping comprise. The virtual address space of a running program, the cell in this example TSCH, okay, or TCSH, I guess. The output shows 4 columns, the virtual address of the mapping, its size, the protection bits of the region, and the source of the mapping. Virtual address of the mapping, this one, the size, and then protection bits here, the permission, I guess, and the source of the mapping, this one. Okay. As you can see from this output, the code from TCSH binary as well as code from libc, libgrep, libinfo, libdinfo, and code from the dynamic linker itself, lt.so, are all mapped into the address space. Also present are 2 anonymous regions, the heap, the second entry Maple anon and the stack, maple stack. Okay. Memory map file provide a straightforward and efficient way for the operating system to construct a modern address space. Okay, I think I've taken a look at the PMap before. Yeah, but I don't remember on which chapter. Probably chapter 20, maybe. Yeah, I don't remember. But yeah, I remember we take a look at this kind of information, I guess. Alright, I think let's continue this security and buffer overflow on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.